Okay, welcome everyone. Thanks to Billy Joel for that intro. Let's get started. So this week we're going to talk about the carbon cycle. We're going to track the movement of the carbon around the planet. So why are we talking about carbon anyway? Well, last time we talked about greenhouse gases. So this is a brief summary of what we did last time. We predicted a model for what a greenhouse gas is, that it has to absorb and emit infrared radiation. And by doing this, it provides the greenhouse effect to our planet, which, going all the way back to our first seminar, we very much need in order for the temperature of the planet to be comfortable for humans and lots of other life forms. So we used a simulation to test various gases, and we learned that the very simplest molecules, two of the same atom, cannot be a greenhouse gas, while more complex molecules, like 3 or more atoms, or having 2 different kinds of atoms, are usually a greenhouse gas. So we're now going to start talking about we left off last time with the sort of big man on campus greenhouse gas, the carbon dioxide. So we're going to start tracking the carbon dioxide, or really we can get even more specific and we can track the carbon atoms themselves, right? And in order to do that, we need a bit of vocabulary. We need to introduce 2 words often used in climate modeling, which are stock and flow. Stock and flow. These are very simple ideas that just have a slightly different name from perhaps what you're used to. Stock is just how much of something do I have? For example, I have a stock of 10 apples, right? It's a measurable amount of something, right? So we're going to be talking about stocks of carbon in a little bit. Whereas flow is a change in that quantity. So a flow is every day I go to the store and I buy 1 apple. So let's consider this example for a moment here. I have a stock of 10 apples, right? There they are, right, in the picture. But every day I go to the store and I buy 1 more apple. What is going to happen to the stock of apples that I have if I'm just buying a new one every day? Does this seem like a good idea? Don't be shy. Unmute yourself. Shout it out.
The number of apples will go up.
Yeah, I'm going to have an increasing number of apples, right? This is an unsustainable apple situation, right? So this is an example where the flow is large compared to and unaffected by the amount of stock. Here is an example where it's balanced. This is an example of balanced stock and flow. If I have a stock of 10 apples, and every day I go to the store and I buy 1 apple, but also every day I eat 1 apple, well, then the inflow of apples matches the outflow of apples, and I will maintain an even stock of 10 apples. Right? So this is the kind of thing we're going to be thinking about when we talk about what's happening to the carbon. And especially we're going to be thinking about this sort of thing a lot next week in our final seminar, feedback loops and tipping points. But for now we've got this terminology of stock and flow under our belt. Let's talk about where is the carbon? Thinking about the planet as a whole, where might we expect to find the largest stocks of carbon? So I want everybody to brainstorm this. The chat is currently set so that you can send messages out to everybody. This is a public brainstorming session. Where on considering the whole planet, where might we expect to find the largest stocks of carbon? I will give you a moment to think about it. Okay, the Earth's crust, subterranean. Keep them coming. These are good.
Okay, I would say in the oceans, but I can't. I don't see the chat.
Oh,
I can't see chat.
you don't have a chat button? Okay, well, we'll assume you type that in.
have a chat button, but it's not doing anything.
Oh,
Okay.
not
Anyway,
sure about that. But anyways, you got your answer in.
okay.
Coal deposits, oil reserves, absolutely. So Tehila says the ocean in life, in trees and in animals. I like that, right? We are, after all, our primary structure. We're a lot of water by volume. But in terms of what gives us solid structure, that's carbon and nitrogen, as far as I know.
And calcium.
And calcium. You're absolutely right. And calcium. So let's write down some of your answers here. Earth's crust and underneath the surface, right? And further down. The ocean. The oceans. Coal and oil deposits. Life made of carbon. So here is a list which is in order from largest to smallest. So the ocean wins, ironically, by a landslide. That's the deep ocean and the surface ocean. Climate models usually make a distinction between the two regions of the ocean by depth. Coming up in second place is the ocean floor itself, then the land, which is fossils and soil, the plants and the animals, which is the biomass, and then finally the one that nobody guessed is the atmosphere itself. So this list is in order from largest to smallest. Most of the carbon on the planet is in the oceans or somewhere in the ocean floor. That's where the carbon is. You can actually see every single example that I just listed in this picture, which is of course taken in New Zealand, because where else would you find a picture like this? So now that we know where the carbon is, that's the stocks of carbon, right? And we'll get to numbers in a minute. We want to know how it's moving around. So now my new brainstorm task for you, now that we know where the stocks of carbon are, let's brainstorm processes that flow carbon between the stocks. How is carbon exchanged between the plants and the atmosphere, for example? That's an easy one. Between the land and the ocean, between the atmosphere and the ocean. So, once again, take any guesses you can make. Put them in the Zoom chat. Transpiration, good. Somebody remembers somebody knows their biology, right? Transpiration. What else we got? What else can move carbon between these things? How do I move carbon around between the ocean, the land, the plants, the atmosphere?
Photosynthesis.
Photosynthesis is that true? I mean, that involve.
Of course, you take carbon dioxide and water and make oxygen.
Yeah, there you go. There you go. Yep. I was the one reading Rusty there. That was my fault. You're absolutely right. So transpiration and photosynthesis, those are two processes that involve the plants. So what about ones that don't involve the plants? After all, the plants are pretty far down the list. What about between the ocean and the land, or between the ocean and the atmosphere? Any guesses there?
Seashells.
You're absolutely right. Oh, yes, evaporation, of course, right? If there's carbon in the ocean and it evaporates, then that will take, and if the carbon is dissolved in the water, then when some of the water evaporates, it'll take some carbon with it. And so there will be carbon gas in the atmosphere, right? So there's a direct change of state exchange between the ocean and the atmosphere. And yes, Tehila mentioned seashells, which we will talk about in a little bit. So here are the list of processes. Plant respiration is one of them. The movement of sediments on the ocean floor. The water cycle itself is part of the carbon cycle, right? All of these cycles are, of course, interconnected and interrelated, right? But as water evaporates, moves around in the sky, it rains, it flows to the ocean. That's moving some carbon along with the water. The birth and death of plants, right? As plants grow, they take up carbon from the soil, they use it, right? They take carbon from the soil and they use it in photosynthesis, right? And then they die and the carbon returns to the soil. So that's an exchange between the plants and the soil. And finally, the other one I mentioned, direct gas exchange between the ocean and the atmosphere, right? So this is evaporation and condensation. Let's take a look at all of this in one picture. Well, okay, technically it's going to be two pictures. We're going to start with one picture. So here we go, right? This is a really nice picture of the carbon cycle. I guess you could say carbon cycles. There's a lot happening here, right? So we've got photosynthesis, where the plants take carbon in from the atmosphere. Plant respiration, where they breathe the carbon back out to the atmosphere. The plant biomass, right? So photosynthesis gives rise to plant biomass and in turn also gives carbon to the soil. Microbial respiration and decomposition will take carbon out of the soil and put it into the atmosphere. Notice that I've covered up the human emissions. We're not talking about that yet. Right now, we're talking about the unperturbed carbon cycle, right? We're talking about what's the natural part of the carbon cycle. So the emission of carbon dioxide from human combustion of fossil fuels has been hidden. I'll show you later. We go over to the oceans. There's the air-sea gas exchange, right? So as water evaporates and condenses, some carbon moves around here. By the way, these numbers are actually pretty big. The numbers in white, so for example, over here it says atmosphere 800, that's the stock of carbon in the atmosphere. And it is measured in gigatons of carbon. So over the whole atmosphere of the whole planet, there's about 800 gigatons of carbon, right? Numbers in yellow are the natural flows of carbon, and that's measured in gigatons of carbon per year. So every year, the entire ocean exchanges back and forth about 90 gigatons of carbon with the atmosphere. Now, in the ocean, you have more photosynthesis, more respiration and decomposition. So there's a whole mini carbon cycle happening on the surface ocean, which contains a stock of about 1,000 gigatons of carbon, more than the entire atmosphere does. And then if you go into the deep ocean, the only thing really happening here is that as ocean organisms die, they sink and they take carbon down to the deep ocean and the ocean floor with them. So this is one of the main ways that carbon is removed from the cycle. The other being the soil carbon, right? As plants die, they become one with the soil and some of their carbon just stays there and some of it becomes fossilized. But the deep ocean has this massive, massive stock of carbon, 37,000 gigatons of carbon. It's a lot. So that's where the stocks of carbon are, and that's what some of the flows of carbon are. There's a little bit of stuff with like coastal exchange that's not really depicted here. But that's what's going on with the carbon cycle. While we're here, does anybody have any questions? This is a big image. It's a lot to take in. You're totally allowed to ask questions.
Yeah, I'm surprised that the plant biomass is less carbon than the atmosphere.
Yeah, go figure, right? The atmosphere is large. It's very large.
Isn't there like a fear that if the oceans like sort of turn over, they'll release like tons of...
Yeah, so I don't know for sure if this is like which scenarios this is a part of, if any, but if somehow the deep ocean started releasing even a fraction of its carbon, we would be in deep, deep trouble, pun intended.
And also when plants mostly transpire during the day,
I believe that's correct.
and they mostly and they almost totally photosynthesize during the day, and that's when they're using the carbon dioxide.
That makes sense.
You're
the expert on that, not me.
No, I'm just saying that I don't understand how transpiration is such a big factor in releasing carbon dioxide from plants.
To me, these numbers here, 120, the plants take in 120 gigatons of carbon per year. and they give out 60 gigatons of carbon per year through respiration, tells me that there's some sort of 2-to-1 ratio that the plants are using about half of the carbon they take in from the atmosphere and then just rejecting the other half. But I'm not an expert on the chemical reactions of photosynthesis or respiration anymore. So
All right.
you would know about that, the details of that better than I do.
All right.
We can
Well,
discuss later.
yeah.
Let's move on. Speaking of respiration, before I show you the hidden numbers, I want to try an exercise. And I want to also show you a graph that I run into a lot because this is one of the best data sources we have about carbon dioxide in the atmosphere. So this is atmospheric CO2 at Mauna Loa Observatory, and they're measuring the carbon dioxide in the atmosphere. They're just sampling the air and measuring how much CO2 they find. And so this has been done. This is high quality, very, very high quality data that's been taken since about 1960. And this graph shows it up through 2020. So this is very up to date. There's a website where you can actually see the live version of this, quote unquote live. And because the atmosphere is, because CO2 is very mobile in the atmosphere, it spreads itself out very rapidly and evens itself out very quickly. The data at Mauna Loa is a pretty good representation of what's happening basically all over the world. So here we see a plot of their data in red. The red squiggly line is their actual concentration data measured in parts per million. And then average trend line in black, right? So the wiggles in the line are corresponding to an annual cycle. And we were just talking about plant respiration and photosynthesis. That's what that annual cycle is. So during part of the year, the plants are photosynthesizing more. And so there's a net loss of carbon from the atmosphere. And during a different part of the year, the plants are respiring more. And so there's a net gain of carbon into the atmosphere. And so here's the exercise I have for all of you. If I were to zoom in on a graph of just, on a graph of just 1 year, which part of the year or which months would the CO2 be decreasing? And which part of the year would it be increasing? And why? And so there's a helpful reminder down here for all of us who are a little bit rusty like me on our plant biology, that photosynthesis takes CO2 out of the atmosphere and respiration puts CO2 into the atmosphere, right? So this is a fun little biology exercise. When are the plants doing more photosynthesizing than they are respiring? And when are they doing the reverse? Let's think about that.
I mean, obviously in the summer, they're doing more photosynthesis because we have more daylight, but depends which hemisphere. In the northern hemisphere, you know.
That's a good point. I think this might be, oh, right. You have to take the hemispheres into account. I remember this now. So we can sort of get away with just focusing on the northern hemisphere, and that's not a colonialism thing. That's just because there's less land mass in the southern hemisphere. So there's less plant mass in the southern hemisphere. So the northern hemisphere trend wins out here. So you think, okay, it's the summer. There's more daylight. There's more photosynthesis in the summer. It's actually a little bit time shifted from that. Here's the answer. So this one tripped me up too when I was first learning about this. It was not obvious. As the northern hemisphere enters autumn and winter, plants slow their growth. So the amount of photosynthesis drops, but they continue breathing. So the result is a net increase in atmospheric CO2 during the fall and winter months. And we see that on the graph here, that if I'm in October, starting in October, November, December, January, February, March, April, all the way up to April and May, the carbon dioxide in the atmosphere is increasing, right? Starting in May, June, July, August, and even all the way into September, the carbon dioxide is decreasing. So actually, Michael, I think you were just bang on correct, which is that from May through September, we've got a decrease in the carbon dioxide in the atmosphere. And from October through May, we've got an increase in the carbon dioxide in the atmosphere. So that's the timing. This is the kind of reasoning that goes into all those detailed climate models we saw at the end of our first seminar, right? Making a valid climate model, or even just refining a climate model, involves pulling all kinds of things together, from physics, chemistry, biology, geology. It's really a true interdisciplinary challenge. All right, now I'm going to show you the numbers I didn't show you before. So you can see there's a square over here, and a square in the middle, and a square over here. There are 3 places on this picture where the effect of humans is seen in the carbon cycle. Here they are. Okay, so now numbers in red are additional flows of carbon due to human activities. And so all of human emissions is represented in the center of the picture as 9 gigatons of carbon per year. 9. Right? And then something interesting happens, right? Which is that we kind of get a helping hand from nature here. The photosynthesis is now 120 plus 3, and the air-sea gas exchange is 90 plus 2. What does this mean? It means that the plants are able to absorb some of the excess carbon that we're putting into the atmosphere. And the ocean, the condensation of stuff that falls into the ocean, is also taking just a little bit more of our emissions extra on top of what it normally does, right? So there's some extra capacity in some of nature's processes that's softening the blow of what we are doing to the atmosphere. So we're putting in 9 gigatons of carbon into the atmosphere every year, but nature is taking care of about 5 of that for us. And so all the global warming and all the climate change that's been happening so far is only about half of what we could be doing to the atmosphere if this weren't happening, which is a sobering thought, to say the least. Here is also a slightly updated version. This one is much more schematic, but it's really the same picture, which is to say I've got the stocks now represented as circles. So dissolved inorganic carbon in the ocean. This is slightly more up to date. That picture was from about 10 years ago. This one is from 2 years ago. There's about 38,000 gigatons of carbon in the ocean. Here's the air-sea gas exchange, the 90 and 90, right? Humans have now been putting, as of lately, more closer to 9.5 gigatons of carbon into the atmosphere every year. Here's the vegetation part of the cycle. There's your 120. Oh, you know what it is? Take a look at this. This says 120 up, 120 down for vegetation. Check this out. 120 in for photosynthesis, 60 out for plant respiration, and 60 out for microbial respiration. So really it is 120 in, 120 out, but some of it goes through the microbes first. That's fascinating. Right? So these are slightly more up to date. Atmospheric carbon is increasing. And take a look at this. Budget imbalance, 0.4 gigatons of carbon per year, right? So that actually seems a little low. I thought the imbalance was a little higher than that. But we are putting more carbon into the we are unbalancing the flow of carbon by about 0.4, right? We're taking carbon out of the soil where it was in these fossilized organic substances we call fossil fuels, and releasing it back into the other parts of the cycle. Will nature eventually take the excess carbon that we're putting into the atmosphere and return it to where it is, what you might call sequestered? Yeah, eventually, in like 50,000 years, right? Nature's processes are slow. And what we're doing is much, much, much faster. So that's the perturbed carbon cycle. This is what's happening to the carbon presently. The next half, give or take, of the presentation is a series of graphs that ask what's happening over time and how does this break down by different types of human activity? So let's first look at what are the primary channels. Oh, Michael, what's up?
So I threw something into the chat.
Oh, let's take a look. I wasn't really looking at the chat.
There's essentially the World Bank has been proposing all these different ways to carbon price. And they're saying that the current carbon pricing schemes cover 12 gigatons of CO2 equivalent, meaning including methane and things like that each year.
Mm-hmm.
And that only represents under a quarter of the global emissions. So they're showing a number essentially that's a lot higher.
I think, let's see. I have your answer coming up. You actually anticipated a question that I thought people would ask. So first, First, we're going to talk about just carbon dioxide, right? And that's kind of part of the answer to your question right there. So how are we doing this? How are we releasing carbon dioxide into the atmosphere? Coal, right? A little bit oil, okay, more than a little bit oil, right? Mainly coal, some oil, a little bit of gas. Cement is there. Flaring. Does anybody know what flaring means? I had to look this one up. What's flaring?
When they burn
Here in
off
the
the
purple.
excess methane?
Yeah, that's the one, right? Other industry, right? Mainly, we're getting it from coal and oil. And so I point out on the right here, coal continues to be the largest contributor to human carbon emissions, despite the rise of oil and natural gas in the 20th century, right? You can see right around here in the year after the year 1900, we started finding petroleum reserves like nobody's business, right? And burning them and processing them and doing all kinds of things. Use of methane as a fuel followed. So that's how we're putting carbon into the atmosphere. And part of the answer to Michael's question is already present on this graph. Take a look at the numbers on the vertical scale of this graph. 5 billion, 10 billion, all the way up to 35 billion tons of carbon dioxide going into the atmosphere. And you say, but wait a minute. Dr. V just said, I thought human emissions were 9 gigatons per year. What's up with 35? Anybody think they know the answer to this puzzler? I just showed you a whole bunch of information saying the carbon cycle, we put about 9 or 9.5 gigatons of carbon into the atmosphere every year. This is talking about 35 gigatons. What's going on? Bob, you know the answer to this one? I just got done talking about 9 gigatons of carbon going into the atmosphere every year, and here I got this graph saying 35 billion tons or 35 gigatons. If it makes you all feel any better, I spent a good 2 hours or 3 hours over this weekend being very, very confused by this. I'll give you a hint.
So you're saying that things like methane, which are a much more potent gas, they're giving you CO2 equivalents here.
That's what I thought too, but it's actually that is some of what we're going to talk about, but actually it's the oxygen, right? This graph here is showing the mass of carbon dioxide, whereas the cycles I was showing before is the mass of just the carbon. And it turns out that carbon dioxide has about 3.5 times as much mass as just its own carbon atom. And so you want to be really careful which is the vertical axis of your graph. A lesson I learned again the hard way. Okay, so now that we've got that sorted out, right, that goes part of the way towards explaining the number you just saw, right? That 12 gigatons might only be 22% of the total. So part of that is that they're talking about carbon dioxide and its equivalents, and the rest of it is the equivalence part. So let's look at the greenhouse gases, right? So this comes from Intergovernmental Panel on Climate Change report from 2014. What are the primary channels by which humans release greenhouse gases into the atmosphere? Before I talk about the breakdown, notice that the total in 2010 was 49 gigatons of CO2 equivalent, right? So some of these emissions are from other greenhouse gases like methane, right? Or nitrous oxide or carbon monoxide. Mostly methane is the big hitter here. And basically what they did is they can say, okay, we released X gigatons of methane. What is that if we had released it as CO2 instead? And they add all that together and they get a number of carbon dioxide equivalent gigatons. And that total came out in 2010 to be 49. And so now we're starting to see how 12 gigatons might only be 22% of the total. In fact, let's do some quick math here. Yeah, 22% of 49 is 10.78. So that lines up rather nicely, especially since this is from the year 2010 and is 10 years out of date, and it's probably a little higher now. So let's see how this breaks down. They break it down first at the bottom into direct emissions and indirect emissions, right? So direct emissions are things that just literally spew CO2 into the atmosphere. Indirect emissions are, hang on a minute, electricity and heat production, especially energy, other energy, industry. Okay, admittedly, I'm not sure why. It seems to me at first glance they have direct and indirect swapped here. But perhaps what I'm thinking of is that this other energy is where most of the burning of the fossil fuels happens. I guess this is all burning of fossil fuels. Maybe that's what's confusing me. Okay, let's undo that. The other thing we want to explain here is AFOLU, agriculture, forestry, and other land use, right? So cutting down trees doesn't just stop the trees from absorbing carbon dioxide, but literally the act of cutting them up releases some of that carbon. So that's part of what's going on here. Buildings, transport being things like you get in your car burns gasoline, that emits carbon dioxide. Industry, other energy. So now that I think about it again, apologies for the confusion, this is likely the energy consumption needed to run buildings, the energy consumption needed to run industry, the energy consumption used for miscellaneous, and then we have the burning of fossil fuels by transport and the effects of cutting down trees, right? And then you have indirect CO2 emissions, which all fall into this category of electricity and heat production. Again, wouldn't that be direct by burning fossil fuels? But I confess I don't know some of the details of how they put this picture together. But this is generally how it breaks down. It's kind of a mishmash, right? We're putting carbon into the atmosphere for all sorts of reasons in all sorts of ways. And this is why I keep telling my students that solving this is not solving one problem, it's solving 1,000 problems in all different parts of the world. You have to have 1,000 solutions, each one tailored to the region and or country that you're implementing it in.
Also, the AFOLU includes meat production because
yes,
cows release a lot of methane by farting, basically.
That is absolutely true, and by belching. Let's not forget that. So you're absolutely correct. Now, over time, what's happening over time? It's getting worse. You can see that on this graph, which I took from the NOAA, this is again a slightly older, but it nicely shows the trend here. Fossil fuel versus volcanic emissions. We didn't specifically set out to talk about the role of volcanoes in all of this. They were present on my other image. No, not that one. This one. All the way on the left-hand side here. The 0.1 going into the atmosphere from volcanoes. That's what they do, right? Volcanoes don't contribute that much carbon dioxide. And so you can see the pink line at the bottom is the annual average 0.1 gigaton of carbon dioxide added to the atmosphere per year. Actually, I'm not. This is in CO2, not carbon. So you would think that would be a little bit bigger than 0.1. Maybe it's at 1, something like that. It's very small, and it's staying constant over the centuries. And somewhere around the year 1825, 1830, you can see the green line representing our emissions from fossil fuels visibly tick up off of zero for the first time. I'm sure it wasn't exactly zero between 1750 and 1830, but this is when you can start to see it come up off the axis. And then in the year 1900, right around the beginning of the 20th century, it really kicks into high gear. Most of the carbon we have emitted into the atmosphere has happened not just during the 20th century, but in the years from 1970 to now, right? This problem has been happening for a while, but within our quote unquote our general lifetimes, within recent memory, it has gotten much, much worse. Here's another. So again, this was carbon dioxide. This was direct CO2, not equivalent. Here's the equivalent graph for greenhouse gases in general. So now we're at gigatons CO2 equivalent per year. And so this is broken down by type of gas. The orange is CO2, fossil fuel and industrial processes. The red is CO2 FOLU, again, forestry and other land use. So that's the CO2 we emitted by cutting down trees and other things like that. The light blue is methane, CH4. The darker blue is N2O. That's weird. I thought we were talking earlier about, maybe it's a different gas. Maybe I should have accounted for nitrous oxide earlier. And then up top in a very, very dark blue, you can only just barely see it until the last 5 or 10 years or so, is what's called F gases, which are fluorinated gases like HFCs, hydrofluorocarbons. These are used primarily as refrigerants in AC units and heat pumps, which is a whole other fascinating topic, because in the United States, at least, the majority of homes that need heating systems traditionally have done this with a furnace or a boiler that burn fuel on site, right? The whole thing, oh, do you have oil fuel? You have oil heating, gas heating, right? There's a much, much more efficient way, which is to say you use less energy to heat your home, which is a heat pump. And a heat pump is an air conditioner literally run in reverse, right? If you ever reached around the back of a fridge, you know that it's pretty hot back there. So imagine the fridge or the AC unit, you're living at the back of it, which is your house, and it's removing heat from the outside and pulling it into your house. That's a heat pump, right? And even though heat pumps would use these F gases, which is theoretically bad, their contribution to climate change is so much smaller than burning coal for electrical heating or burning gas and oil at the site of your home for to run a furnace. It would be environmentally better if houses switched to heat pumps, and then we could sort out better refrigerants down the line, right? That's the sort of buying time solution that needs to start happening in a lot of places. Okay, let's pause and reflect for a moment before we go on to the final part of the evening seminar. Questions, comments, other thoughts? existential crises.
Can I ask a question about the heat pumps?
Absolutely.
Is it because they're more efficient or just because they're used less? Like,
I think it's a little bit of both, but mostly it's the efficiency. A good heat pump will take in from your electrical grid 1 unit of energy, and with that 1 unit of energy, it will move 4 units of heat energy into your home. That's how good they can be.
mhm.
Can I ask a couple of questions on the slide, a few slides back about?
Sure.
It was the one where it was a very pretty slide where you had the 90+3 and you were showing how nature
This one.
is. Yeah, that one's really cool. So I have a couple of questions on this slide. As nature is taking in some of it, so on the air-sea exchange, for example,
Mhm.
there's an extra 2 coming in. Does that have ramifications on the other side of that 90? Does that become 90+2 also? And
You'd
are there any
think.
negative ramifications for that?
I think what's happening, quote unquote, for now, which is to say within the last few decades, is that the stock of carbon in the surface ocean is simply increasing. And it's not immediately coming back out as an extra +2 on the other side. That in turn does have consequences for the ocean, because with more carbon in the ocean comes more ocean acidification, right? And this is where you hear about like the coral reefs having trouble in the past few years, right? You get all kinds of like carbonic acid forming in the ocean, extra carbonic acid that it didn't have before, and so that's bleaching the coral reefs, which is bad. Eventually, other things would start to happen, and I imagine there would come up there would come a point where carbon would start to outgas faster from the ocean, but that is where my expertise in ocean biochemistry ends.
Got it. So even the so-called benefit that we get from nature, where it seems to be able to accommodate
Right.
about half of our carbon,
Even that comes with a
emissions,
cost. You're right.
really also comes with a cost. And
Yes,
then-
that too. Yep.
Okay, so I don't have any more questions.
Okay.
Answers-
Let's go on to the
answers
final
other
part
questions that I had.
of our presentation,
Dr.
which
V, Dr. V, I have
yes,
a question for
Tehila.
you. As long as you just have that slide, the
Yeah.
same slide. Okay, so maybe I'm being like really simplistic, but if we were able to cut down our emissions
Mhm.
by 50%,
Yeah.
looking at this graph, would that solve our problem?
It would certainly be a very good thing for us to do. My understanding, and I'm like 90% sure that this is true, is that as our emission of carbon into the atmosphere has increased, these quote unquote accommodations from nature have more or less consistently absorbed half of it. So my first answer, and I could be wrong about this, is that if we went down to 5 gigatons a year, nature would absorb about 2.5 of it. I don't know exactly why that should be, but I think that might be what's happening. Certainly, we should endeavor as quickly as possible to cut all of our emissions to 50% and then to 0 of our current levels. But yes, I don't think it would absorb all of it, nor do I think we should allow this to be the general state of things, because as we just pointed out, allowing the ocean to absorb excess carbon creates problems for ocean ecosystems, which in turn creates problems for every other ecosystem on the planet. All right, let's go to the last part of our presentation, which is sort of starting to get into the material for next week as well. We're going to think through an example of feedback. So what I showed you over here is actually called the fast carbon cycle. This is the stuff you can measure in gigatons per year. There's also a slow carbon cycle. There are a number of processes not shown here, which are very, very much less than gigatons per year. And we're going to look at one of those processes now, which is called weathering. So weathering is the name for a natural geological process, and that right there is a clue to how fast it happens, that removes CO2 from the atmosphere. Okay, so it goes like this. There's some CO2 in the atmosphere. There's a stock of carbon in the atmosphere. Some of that will be absorbed into raindrops when there is rain. Okay, so there's rain. It's got some of the atmospheric CO2 in it. When the rain falls, the CO2 strikes igneous rocks on the landscape, right? So again, not all of the rain is going to hit igneous rocks, but some of it will. The CO2 and the igneous rocks undergo a chemical reaction, which creates sedimentary rocks. So we're talking about converting igneous to sedimentary, which again, geological process. This takes many, 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 many thousands of years. The carbon from the CO2 is stored in these new sedimentary rocks. And then gradually, through weather like wind and more rain and waves and erosion, these sedimentary rocks are washed out to sea where they are buried in the sea floor. And thus we have a flow of carbon from atmosphere to rain to rock to other kind of rock, all the way out to sea and down into the sea floor. So here's the logic. If there is more CO2 in the atmosphere, then the atmosphere is warmer. If the atmosphere is warmer, the amount of rainfall is increased. If the rainfall is increased, the weathering reaction occurs slightly faster. If the weathering reaction occurs faster, then the amount of CO2 in the atmosphere will decrease. Does this make sense?
Yes, but it's still slow.
It's still very, very slow. Would that this reaction were 1,000 times faster than it actually is, right? Then it might really save our butts. But this is much too slow to rely on to rely on as a fix for the climate crisis, right? This is what I mean when I say nature will eventually remove the excess carbon from the atmosphere millions of years from now, right? That's how long this is going to take. So this is an example of what we call feedback, which is another important climate modeling idea, along with stock and flow. So the feedback, in a nutshell, an excess amount of CO2 in the atmosphere increases the rate of the weathering reaction, which in turn decreases the amount of CO2 in the atmosphere. And so we can define, using this example, define feedback in terms of the ideas of stock and flow, where we say that a feedback or a feedback loop, if you're feeling fancy, is any process where the amount of stock influences the amount of the flow, right? More CO2 in the atmosphere, slightly faster rate of removing CO2 from the atmosphere. That's an example of feedback, right? So we're going to talk about all kinds of feedback loops and tipping points in our final seminar next week. We have plenty of time for other questions about the massive dump of information I have given you over the past 50 minutes.
So, Victor, does that mean that when it rains and it brings that carbon down into the rock, which then washes out to sea?
That's right.
So does that mean that we're dumping carbon at the bottom of the ocean?
Yes. Our excess carbon is coming out of like the deep, deep crust, like way under the bedrock. And so what we've been doing as a species is pulling carbon out from way underground and putting it literally everywhere else that you can possibly imagine the carbon is going. Carbon is very, very mobile on this planet. It gets around fast. So it's going in the air, the water, the plants, the life, the ocean, every part of the ocean floor, all of it.
Yeah, and can I ask one other question?
Absolutely.
At the beginning, I don't remember exactly how you worded a bunch of things, but is what you're saying that at the beginning you were talking about just carbon?
Yes.
And then later you realized
Right.
the reason that some of the data didn't seem to comport with what you were saying later is that later they were talking about carbon dioxide and methane and
right.
carbon.
So people talk about carbon and the carbon cycle and greenhouse gases in multiple different ways. And you just want to make sure you know what you're looking at. Oh, so there's a question in the chat. I will get to that in just a moment. Basically, if you look up the carbon cycle, you will find pictures like this one, where they talk about the mass of just the carbon. And so you see numbers like, oh, correction. You see numbers like, oh, hang on, there it is. You see numbers like 9 gigatons per year, or 9.5. Right? That's what we found in this picture here, which came from a recent research paper, 2019. If you look up other sources that are talking about the movement of, that are talking about climate change, right? They tend to use gigatons of carbon dioxide equivalent. And so there's two changes there from what the other pictures were showing. First of all, carbon dioxide versus just the carbon. That's our first multiplier that makes the number bigger. And then CO2 equivalent, which means now we're also folding in methane and carbon monoxide and all those other delicious greenhouse gases, right? So that's what was going on with that. Could you please go over that chart of total carbon equivalents again, the one with the fluorogases? That would be this one here. So if we look over time, oh, you know what I didn't point out about this one last time is the time range. The first graph I showed you over time goes from 1750 to about 2013 is when this graph was published. This one goes from 1970 to 2010. And you can see that quite a lot of greenhouse gas emissions occurred over those 40 years. So it's showing us that in the orange we have CO2. And so we went from about 15 gigatons of carbon dioxide in 1970 to over 30 gigatons of carbon dioxide in 2010, especially if you account for the carbon that was emitted through forestry and other land use.
This is 70.
And I suspect if you just look that number up, you'll find the one that includes the carbon, the forestry and other land use, right? So you'll find, for example, on this graph was talking about 35 gigatons of carbon dioxide. And I don't see that on this graph unless I include the red part. And that gets me to about 35, right? But if you break it down between what's used for fossil fuel and industrial processes versus forestry and other land use, that's where you get this red-orange split. Then the next layer, I have methane, CH4. So we emitted about 5 gigatons of methane into the atmosphere. Correction. The amount of methane we emitted into the atmosphere in 1970 was equivalent to about 5 gigatons of carbon dioxide, which means it was actually much less than that of methane, because methane is very potent. And that has actually fallen a little bit. We've managed to not increase our methane emissions, at least not much, or maybe even they decreased a little bit. So that's a silver lining. Followed by, in the darker blue, N2O, which I believe is nitrous oxide, but there's a chemist on the call who can correct me if I get that wrong. And then at the very, very top in the very dark blue, we have F gases, which are fluorinated gases. So that one example of that is a category of gases called HFCs, hydrofluorocarbons, not to be confused with CFCs. F gases very specifically exclude chlorofluorocarbons. And I think the reason is because chlorofluorocarbons, while bad, are not a greenhouse gas, or at least don't produce a substantial greenhouse effect. But HFCs are a greenhouse gas. Okay. Michael, what's up?
So I have a question that I don't expect you to answer now.
Okay.
But
you can give me homework.
I'm giving you homework for the next week, if that's okay.
Yeah.
Which is, we've been focusing on Earth, basically on the greenhouse effect here.
Yep.
And what I'll say climate skeptics throw in as one of the causes, and this is why I don't expect you to know this, because you're not going to, because it's not necessarily the answer, but I'm curious, I want to get it debunked, is that the sun has actually produced more output recently because of solar storms and things like that. So therefore, there's
Hmm.
more radiation hitting the Earth today than, let's say, there might have been 20 years ago or whatever it may be. And that's accounting for recent warming.
Okay.
So in other words, does
Right. The short answer is no, that does not account for recent
Okay,
warming.
well, that's
But
what
I
I'm
will
asking.
give you a full answer next week.
Okay, because I guess their argument, and I don't know if it's a correct argument or not, I'm assuming it's not, is that there's a slight amount of extra solar radiation hitting us,
Mm-hmm.
and that, quote unquote, more than accounts for the temperature rise versus whatever might be retained greenhouse wise.
Hmm. Yeah. I mean, of course, there's the really easy counter argument is, well, shouldn't we do all this stuff in that case anyway?
No, that's fair. Well, I'm going to give you a follow-up question if that's
Yeah.
okay.
Yeah, of course.
My follow-up question is, we're focusing on the anthropogenic carbon, if you will, meaning
Yes.
that we have control over.
Right.
But, and I'll go back to something I mentioned first. If we look back in history, there are times in history where the Earth is covered in ice,
Correct.
and there are times in history where the Earth is covered in palm trees.
Yep.
And so we've had temperature variations in history that have gone to real extremes. And I guess the question is, here we're focusing on what man is doing to it and creating, a pretty rapid change in geological terms. But do the climate scientists try to figure out, okay, historically, what has caused these massive changes?
Yeah, absolutely.
Okay.
So they do. And what was I gonna say? I think I was gonna pull something up as an answer to your question, and then I realized it wasn't really the answer to your question.
It's okay to answer them next week. I don't expect you
Right.
to have this at your fingertips.
Okay, hang on. I'm gonna write this down. Let's see. All right. So increase in solar radiation, question mark, and then something about what is it exactly you want to know about these natural cycles of warming and cooling on the Earth?
So in other words, what we are doing now is we're trying to fit, what we think is the cause of a rise in temperature of a degree and a third over the course of a century or thereabouts.
Uh-huh.
And there have been times in history where the temperature has moved. I don't know if it's moved as rapidly, but it's moved directionally a lot.
Right.
Without man doing anything because we weren't around.
Correct.
So, other than, an asteroid hitting the Earth, which has its own issues, do they try to, do scientists, and not necessarily the same climate scientists, but do they try to figure out, okay, this is what caused the ice age or the heat age way, way back. And therefore, I guess trying to see whether what's happening now fits any of those models in any way or not.
Oh, I can give you an answer to that right now. This is already a solved problem, at least back to the past million years, and it doesn't.
Okay.
I can give you some more detail on that if you'd like.
Age, in geological terms, the ice age was yesterday. It was 20,000 years ago.
Correct. So there's a number of methods that scientists use to reach back into Earth's climate history. My favorite is the ice core sample. Dig really, really deep into the Arctic polar ice that's been frozen there for hundreds of thousands of years. Thaw a little bit out. Do a gas measurement. You can get a pretty good measurement or estimate of how much carbon was in the atmosphere, what the atmosphere composition was like at that time. And these cycles, these natural cycles that you're talking about, the ice ages and the warming periods and so on, they happen over the course of 100,000 years. And that's the difference, right? What we're doing in 150.
Yeah. Okay.
I can dig up some sources on that if you'd like for next time.
If it doesn't impact the rest of the class, sure.
I promise it's not going to be on the quiz. Sources on deep climate history. Cool. Andrew, you've been very patient.
Sure, this should be quick.
Yeah.
You have the two charts showing a very sharp increase in emission over the last 4 or 5 decades. But observationally, haven't things gotten a little bit better recently? We don't have the acid rain that we had, a couple of decades ago. It feels like maybe nature is helping out, or am I just wrong about that?
I would say yes and no. I would have to look into the acid rain thing. I feel like you're right. I do remember not hearing so much about the acid rain. I do think it's still a problem in some areas. So I'll have to look into that. But in general, the picture is worse now than it was even 5 years ago. Yeah.
But when you say that observationally, like, is the weather worse now than it was 5 years? I understand that it's worse because there's a lot more carbon in the atmosphere. But have we actually experienced the effect of that yet?
Oh yes, it's already happening. More hot days, more extreme weather phenomenons, once in a century storms happening once every 2 years or once every 3 years. Yes, climate change is not 100 years from now. Climate change is here and now, is already happening. The Earth has already warmed by, I think, 0.8 degrees Celsius on average over the whole planet, and the ecosystems around the planet are feeling it. To say nothing of the acidification of the oceans, coral reefs we mentioned, but also the rising sea levels, right, are already threatening coastal communities. I mean, if you look up, day flooding is a thing now in Florida. Just regular old sea coming on up anytime it feels like it, because the sea level is rising. And that's because the ocean is getting warmer. So yes, these things are already happening. And they're going to get worse before they get better.
Thank you.
Yeah. Any other questions? What a fun note to end on.
So N2O is nitrous acid, which is also laughing gas. Gas. Okay. So laughing gas, that's a good one. So laughing gas. So I'll end with this thought.
Yeah.
I have the solution.
Okay.
From what I learned today is that we need to get the carbon. The only place where this carbon is really safe, this excess carbon, is deep in the earth. It can't be in the ocean and the air. We needed to get it back into the earth.
Right.
So we need to get shovels and different kind of things and just go bury it in the earth, and we'll solve the problem. Because that's what's got to go.
Problem is you got to pull it out of the air first.
Yeah. Well, okay. So we got to get a vacuum and whatever, and then just shove it into the earth, and we'll solve the problem.
So there are companies now that are looking to make a good business model out of literally using chemical reactions and catalysts and good surface area to pull carbon, direct carbon capture, right, out of the atmosphere. And then using other chemical reactions, they can sequester the carbon in a man-made way in a solid object, right? And then that solid object can be buried into the earth, right? Put into a vault, something, right? Can even be used in a limited fashion, right? Instead of digging up new petroleum and burning that, we could make stuff out of the carbon that we pull out of the atmosphere, right? And I'm cautiously optimistic about this. There is a question of like economy of scale, right? Can this new carbon capture industry really gain a foothold? Can it be big enough to make a difference, right? I think we're going to need it to make a difference. I think we are past the point where just reducing emissions is going to be enough. And hopefully the powers that be start to put some laws and some regulations into place that enhance or mandate this carbon capture.
Yeah, so I was saying it was a joke, but I guess it's...
You're not wrong. You're not wrong. All right, let's call it there. I will see you all next week for feedback loops and tipping points. Thanks all for coming.
Thank you.